Okay, today is video 2, and we're going to talk about reading regression output, and then we're also going to learn how to construct an interval for slope. So we're going to learn how to do all of that today. So the first thing I'm going to do is point out some things that are really important in your regression output if you don't remember. So the first thing I have here is your y-intercept, and it's going to be on the row that says constant. And then we also have our slope, which is the coefficient of our explanatory variable, which is drop height. So that's sort of how you can remember that. The next thing is S, which is the standard deviation of our residuals. So it kind of tells you the average size of your residuals. R square, if you recall, is going to be your coefficient of determination, and it basically just tells you the percent of variation in Y that can be explained by the model with X. So obviously that's really important. The next thing is your standard error of the slope, which we're going to be learning about today and learning how to compute it if we don't have the computer output. We're also going to learn how to use it in the interval, so that's obviously important. Now, the way I remember this is if you see standard error, the symbol here, and if you go over to the label here for the row is drop height. So this is standard error of the slope. So that's how you're going to remember that. I'm blocking all of this out because we really don't use it. This would be used if we were doing inference for the y-intercept, which we are not. We don't ever really use the adjusted R-square, so I'm blocking that as well. These two values here, your t and your p, we will use, but later. So I'm going to talk about those at a later point. So let's write out our least squares regression line. And of course, we need our y-intercept, and then we need plus the slope times the explanatory variable. So it's going to be flight time, which is your predicted flight time based on the model. And you have your slope here, your intercept here, negative 0.03761 plus your slope of 0.0057244 times your drop height. And if you write your model this way, you are basically explaining what you're using as your x variable and what you're using as your y variable. So that's obviously important. So because our slope is 0.005724, we estimate that on average the flight time will increase by about that amount, and it's in seconds for each additional centimeter of drop height. So if you remember from chapter 3, as x increases by 1 unit, the predicted y, I should say, will increase or decrease by the slope. So that's interpreting your slope. We need the y-intercept, which is negative 0.03761, to draw the line and to make predictions. But here it really doesn't have any statistical meaning because you cannot drop a helicopter from a height of 0. So it really doesn't have much meaning. However, it sort of makes sense in the context of this problem because you would expect the time to be close to 0 if the height is 0. So S is also really important. We have 0.168181. So that's the average or the typical size of the prediction error. It's basically on average how far is your prediction from the actual or observed time. So that's kind of what we're dealing with there. Now, how do we construct a confidence interval for beta? And it's the same thing that we have used over and over. It's on our formula card, but it's not very specific. So this will basically just give you kind of your thought process behind forming the interval. So you have to have your statistic, which will be our slope, and you have to have your critical value. Now slope, we will use the t-distribution. So your critical value here will be from your t, it'll be your t-star. And then your standard deviation of the statistic, which is your standard error of the slope, which we talked about in the prior page. So where are we going to get all this information? Well, the slope we'll either get from running the regression or we will get it from computer output. T we will find from inverse t, just like we've always done, or we can use a table to find the critical t. And then standard error of the slope, we're going to find it a couple of different ways, or there are a couple of different ways to find it. So kind of just labeling everything here, and I want you to do the same thing on your paper. So we have standard error of the slope, and that is computed by taking your S, which is going to be the standard error of your residuals. And there's two different ways to find that, from the computer output like we just did, or if you actually have the data, you can enter the data and run what's called linreg t-test or linreg t-interval, and it will be the S from that output. And we actually use this sum in Chapter 3 to help support what we were doing. Now, if you're using the formula, this is simply going to be the standard deviation of X, and you would get that from one bar stats. And then N, of course, is your sample size. So standard error of the slope represents how far we expect our estimate to be from the truth in repeated sampling. So this is really important to understand what this is, because remember, we're talking about a sampling distribution of all of our slopes from all the possible samples of that size, and we want to know on average how far we expect our estimate to be. And then the critical T is going to be found the same way we have in the past, except now we have n-2 degrees of freedom, or n-2 for the degrees of freedom to find your critical T. Okay, so let's go ahead and construct this. So we have 70 minus 2 because there were 70 helicopters, so we have 68. Now, for this example, I'm going to use the table B, and I'm going to use degrees of freedom of 60. Because remember, if 68 is not on the table, you have to drop down to the lower degrees of freedom, the next degrees of freedom down from there. So we're going to use T star of 2. So just filling everything in, we have our slope, we have plus and minus 2 times the standard error from, or of our slope, and that's from the computer output. So all of this is from the computer output. Now, if you have data and you're given data, you can use the linreg t-interval for this. However, for this example, we didn't have the actual raw data where we can enter it into list 1 and list 2, so we had to know how to read the computer output. So you're going to have to be able to do that. So we are 95% confident that the interval from, and of course it's just this interval here, 0.0053208 to 0.0061280 seconds per centimeter captures the slope of the true regression line relating the flight time y and drop height x of paper helicopters. And if you notice, everything is worded in a way that explains exactly what the model is using. It's using x of height, it's using y of flight time, and it's a model relating those two things. So that's really important. You need your units. So make sure to include all that when you do your homework and your assignments. Okay, so this is the problem that you're going to do tonight. You're going to bring it to class. So I just kind of want to walk you through a couple different things. So we have here NEA change, which is going to be our explanatory variable, and it's in calories. And fat gain is our response variable, and it's in kilograms. So be careful when you're entering your data that all of these values here are your x's, and then you have to skip down to like 2 lines down, and those are the rest of your x's. So there's every xy pair here, and just make sure you enter all of the first row and all the third row as your x's, and all the second row and all the fourth row as your y values. Okay, because we have not done a full state plan do conclude, I went ahead and gave you the state and the plan part. So I want you to read through this. I want you to learn from this to make sure you could do it the next time. But we're going to construct a 90% confidence interval. So be careful with your T star. You'd find that using degrees of freedom minus n-2 for your degrees of freedom. And then there are some graphs you're going to need to do so that you can do your conditions. Now we have done the conditions, so I feel confident you can do those. I want you to do a scatter plot, a residual plot, and also a normal probability plot of your residuals. So the scatter plot is obviously just x and y. The residual plot, you will actually go back in and you'll use your residual list that your regression will give you. So you use your residuals there, and same thing for the normal probability plot. So you will use that output from the actual regression, and remember it's the resid file that we use for that. So the only other thing that's going to complicate matters for you guys is going to be finding the standard error of your slope. So I want to remind you that standard error of your slope is just going to be SE sub B. And since we don't have computer output, we're going to have to compute it by hand. We'll get the S, and the S will come from when you run len reg t interval. And then S sub x will come from when you run one variable stats. And then, of course, you're going to have your square root of n minus 1 here. And that's just going to be your sample size. So you will compute that by hand. Now, obviously, I'm telling you to go ahead and run the len reg t interval. But as always, I want you to set up the formula showing all the inputs to the formula, so that is why you need this information here. So complete this, and we will check this tomorrow in class.